Good day, everyone. You are welcome to our teaching series for SS1 Physics. In this video, I'm going to be taking you through some measuring instruments and the terminologies used in this measuring instrument. At the same time, we are going to be looking at the errors that can be encountered in using this measuring instrument. So, which means at the end of this lesson, you should be able to explain the concept of least count of an instrument, accuracy of an instrument, the precision of an instrument, and the major errors that we can encounter in using the instrument. At the same time, you should be able to know how to uh, analyze a significant figure, the order of magnitudes of the physical quantities we have. Now let's proceed. Now, what do you mean by least count of an instrument? When we mean least count of an instrument, the smallest value that can be measured by that instrument is called the least count of that instrument. It's also known as the resolution. Now, if you look at your ruler is calibrated in millimeter. So you can see the smallest tiny measure, that is the tiny calibration you can measure with your ruler, which is, it might be the thickness of a thick paper. That is what we mean by millimeter. If you look at it, it's very small, and that is why the least count for a ruler is 1 mm, 1 millimeter, and why that of vernier caliper. You'll be familiar with vernier caliper to measure a very tiny things like the thickness of paper. The least count of vernier caliper is 0.1 meter. These are just the measurement. These are instruments used in measuring length of an instrument. So that of micro screw gauge is 0.01. That one is more accurate. It has more accuracy than all these least the ruler and the vernier caliper, that is micro screw gauge, can measure a length that is as small as 0.01 millimeter. Now we have that of weighing balance, like the one we can use to measure masses. Weighing scale, the least count for such weight scale is 1 kg. It can measure the least, that is the smallest it can measure is 1 kilogram. While the electronic balance can measure as small as 1 gram. For time, the least your wristwatch can measure is 1 second, while the least your stopwatch can measure is what? 0.01 seconds, which is, it will give you more accurate measurements. Now, what do you mean by accuracy? I've been mentioning accuracy since morning, and what does it mean? It means the closeness to the measurement to true value of the physical quantity. The closeness to the, it refers to the closeness of measurement to the value of the physical quantity. Now, let's take for instance the true value of a mass is 25.67 kg, and if we have two students who measure, let's say student A measure 25.61 and student B measure 25.65 kg, you can see student B is more accurate, at least close to the actual value, which is the true value. Now, what do you mean by precision of an measuring instrument measurement? When we mean precision, this refers to the limit, that is the detail. When we say something is more precise than the other, so the one that gives us more details about that measurement is what we mean by the precision, the good and the most precise, or the most precision. Take for instance, we have student A, B, and C having their measurement of time to be 3.6 seconds, 3.69 seconds, and 3.695 seconds. You can see the one that gives us the most precise value here is student C with 3.695 seconds, which gives us the accuracy of at least 0.001 seconds. So which means instruments that have the lowest least count value, we have more precision. That's what you should learn from here. Now, what do you mean by significant figures? This refers to the total number of both the digits, the reliable digits plus the uncertainty digits, which are directly obtained from a particular measurement. Now, significant figure SF. Now, how do you count significant figures?
Now we have rules. The rules are all non-zero digits are significant figure. For example, if you have 16 have 1 and 6, which means there are two significant figures. Look at 36.5. There are three significant figures there. They are all non-zero. Now, if peradventure we have zeros, we find zeros between two non-zero digits like 205. You see, there's a zero between 2 and 5. The zero will be counted as a significant figure. That's why we have three significant figures in 2.05. Now look at the other one, 60.005 has 5 significant figures. That is 1, 2, 3, 4, 5. Now Rule 3 tell you that terminal zeros of a number without decimal are not significant figure. If I have a number without decimal, that last zero or any terminal zeros we have, even if you have more than one zeros at the back, we don't count it, except except it is specified by least count. For example, they give you plus or minus 1, you can now count it. Take for instance, we have 3050. We will not count that last zero, and that is why it's 305, because that zero we have, the zero we have in the center is counted, but that last zero is not counted as a significant figure. So we have 3, while the other one have 2 because of this least count specification. Now all terminal zeros after decimal point are significant figure. So if not, you wouldn't have you wouldn't have write it. Look at it. You don't need to write it if you are not going to count it. So now that you have written it, you have to count it as part of the significant figure, even though it appear at the back of after decimal point, you still need to count them. So that is why 64.00 has 4 significant figure, 25.060 has 1, 2, 3, and 4. The last zero is not counted. Last zero is counted, and that's why we have 5 significant figure here. Now, rules for counting still continue. Now, if the number is less than 1, let's say 0.0 something, you still count. The 4 zeros are not counted. You don't count them. And that is why this one has 2 significant figures, because these zeros are not significant, but 6 and 4 are the 2 significant figures. 2050, they are the 4 significant figures. 2050, even this 0 fall in between two numbers, two non-zero numbers. Why this one fall after decimal point? It is a terminal zero after decimal point, so it is counted, and that's why this one has 4 significant figures. Now, what do we mean by error? Error is bound to occur when you perform experiments, which means there's going to be a slight deviation between the true value you are going to get and the what's it called, and the measured value. So the difference between the true value, which is the actual value, and the measured value is called the error. What do you mean? It means that error is equal to actual value minus measured value. So you take the magnitude of that, or you take the absolute value, which means error is always positive. That is the meaning of these two terminal what's it called, boundary that we put. Now, types of error. We have 3 types of error. We have the systematic error, we have the gross errors, and the random error. What do you mean by systematic? Systematic error arise due to flaws in experimental system. System might involve the observer, the measuring instrument, and the environment you use for your experiment. Systematic error are classified into 3. Now, let me tell you something. This error that we call systematic error can be eradicated by looking for the source of error, by analyzing the source of error, and you can eradicate such error. Now, we have 3 types of systematic error. We have the personal errors, which involve the observer itself. We have the measuring instrument error, which we call the instrumental error, and we have the environmental errors. Now, what do we mean by the personal errors? This involve you not being able to use the apparatus well. Now, look at the way some people look at ruler. Checking ruler measurement, they check it from one side or the other side. This is called parallax error. Now, you are going to encounter an error called the parallax, due to parallax. But if you look at it directly vertically, that is, you look at it straight, and you have already avoided that such particular parallax error. Now these errors arise due to faulty procedure. That is when you don't follow the procedure in measuring what in your experiment. Now we have the other one when you have a faulty instrument. That is instrumental error. This is an example of such instrumental error. Look at it. When this particular pointer is supposed to point 0 when you have not started reading, and this one is not even pointing 0. This one is this is positive 0 error. Why this one is negative 0 error? Is caused by the instrument itself. Now, when we say environmental error, what do you mean by environmental error? This will happen when you do your experiment, you perform the experiment in a wrong environment, which means when you want to take your practical, you have to close all the windows, you have to maintain good temperature and so on. Anything that arises due to all this, like your wind and everything, are called the environmental error. Now, gross errors are, that is number 2. We have the gross errors, which we cause by mistaking, that is mistake in using instruments, recording data and calculation. Instead of writing 2.5, you now write 2.50. You are bound to have such gross error. Now random error, no one can even tell where random error comes from. So you don't know the source of a random error. So it just occur just like that. There's no way you are bound to have this error in your experiment. Now, this, when we say order of magnitude, we can estimate the value of any given number by just the order of magnitude. Now, to get this is the approximate size of something. When we say, well, how large is that book, or what is the quantity of that book, you can say it's, you can just estimate. Now, to estimate such, to round it off, you round the coefficient of a, this a that we have here, 10 raised power minus 10, 10 raised power m. You round a to 1 if a is less than 1, or if a is less than 5 or equal to 5 itself. But you round it to 10 if it is greater than 5. Now, for instance, when we say the mass of an electron is 9.1 times 10 raised power minus 31, 9.1 is greater than 5, and that is why we round it up to 10. That is 10 times 10 raised power minus 1, and that is going to give you 10 raised power minus 30 kg. So if I want to tell you the magnitude of the mass of an electron, I will say it is approximately equal to 10 raised power minus 10 gram and minus 30 gram. Now, mass of universe, 1.6 times 10 raised power 53. 1.6 is less than 5. That's why we round it off to 1. 10 raised power 53, and approximately you can say the mass of that universe is 10 raised power 53 gram. At the end of this lesson, you should be able to solve these questions, and the questions that follow, and submit them to your in order for you to proceed to the next slide. Thank you very much for listening.